Hi everyone, welcome to the Learning on Graphs and Geometry reading group. Today we have Clément Vignac presenting his paper Top N Graph Generation, where he finds some problems with graph generation so far and proposes a fix to have a new, better method for graph generation. If you want to join the reading group sessions yourself, the information and links are in the description.
Yeah. Feel free to interrupt me, ask questions, complain, comment. So that it can be less boring. So the problems that I address is set and graph generation. Okay, so of course there are many potential applications, but the biggest ones that people are interested in, it's molecule generation, and there are many approaches to molecule generation. One is to predict directly the molecular graph, like the adjacency matrix and the edge and node features. And another approach is to predict the conformer, so the molecule in 3D. And in this case, most of all, you want to predict the location of each atom. So in this case, you want to generate a point cloud or a set.
But I'm right in saying that you're addressing set generation and point cloud and graph generation in general here, and but you're saying that just maybe the coolest or the most common application for this right now is molecular graph generation.
Yes. Okay. But indeed the work is for general. Could be applied to general generation.
Okay, but then let me add to the motivation that this graph generation is super cool, because then we can, or molecular graph generation is super cool, for example, or this application, because then we can generate many molecular graphs and maybe optimize towards graphs that have certain properties with some reinforcement learning methods, or maybe we can even optimize or condition the generative model on some properties and then generate molecules with specific properties. Yeah, and then you can have a new drug or something. So that's cool.
Yeah, absolutely. So if you want to, okay, you will understand soon that generating a set or a graph is very close, and I will treat them together. And if you want to, let's say, to generate a set, you need to decide what is your input. And your input could be a latent vector, it could be a latent set. And if you want to generate a graph, you can have a latent graph. In this presentation, in this work, I focus on a latent vector. So the problem is that you have a vector and you want to learn a function that will map it to a set or a graph. You will understand as well that it's a bit easier, at least theoretically, to work with a latent set or a latent graph, but sometimes you really need this vector. For example, as Hannes said, if you generate molecules, probably you want to condition on some properties. And if you constrain the solubility and polarizability of the molecules, then this is a vector that you want to condition on. So my goal is to understand what people did on this topic, try to formalize the problem a bit. We'll see that at first it's not so clear what equivariance properties we want in this setting. And this is something that I worked on. And you will see that the difficult step is to create an initial graph or an initial set. And I propose a new method for this, which is called top N creation. So I will focus on one-shot generation as opposed to autoregressive generation. So autoregressive generation, it had atoms or node or edges one by one. And in one-shot generation, you want to do everything at once. And it's if you do one-shot generation, then it means that somewhere you have a first layer that is going to turn a vector into a set or a graph. Okay, now I will focus on set for now, otherwise it's a mess if I say set or graph every time. So all the layers until this one, I call them the set creation layer. And the layer afterwards, I call them the update. Yes, Hannes?
Yeah, and so is there any case when we get an advantage from autoregressive generation instead of autoregressively generating a set seems bad? like we add an arbitrary order, right? So is it ever better in some way, or are there maybe some applications where autoregressive set creation is better?
For unconditional molecule generation, I would say that autoregressive methods are state of the art right now, especially the fragment-based one. So in this case, you don't add atom one by one, but fragments one by one, but the model is similar. So there is this ordering issue with autoregressive methods, but it's easier to design.
Yeah. Okay, but now you were saying you split your one-shot graph generation into 2 steps, like the set creation and
the update. So the update is once you have an initial set, then you want to transform it into a new set. And in the end, so all this, of course, internally, you don't really represent sets, you represent matrices. So in the end, we have a function which takes the matrix and it maps it to the multiset, corresponding multiset. Dominique?
Yeah, I just want to add here, like when you create a molecule or generate a molecule fragment by fragment, one of the advantages is that it resembles more how like chemists will assemble a molecules, and sometimes people can use known reaction to do the assembly. So that's one of the main advantage here. But the advantage of like generating at one point is, like you said, like there's a problem of the ordering, and there's also like a problem with like the optimization by like building one block by one block. The properties of the graph can change massively between each time you add a fragment. So I think like from machine learning perspective, the second option makes more sense, the generation at once. From a chemistry perspective, the first one has more advantage. When you do machine learning for drug discovery, I guess like both of them can be used in parallel. They don't have to be concurrent methods necessarily.
Mm. Absolutely. Thanks. So yeah, all the existing methods, they fit into one of these 2 graphical models. What is the difference between these graphical models? Well, it's the fact that if you want to generate a set or a graph first, you need to decide on the number of nodes that you want, because it's one shot. You cannot decide on the fly. And to pick a number of nodes, either you can sample from the training distribution. This is the first graphical model. Or you can learn the number of points from the latent vector. This is the second graphical model. So that's the 2 ways to pick the number of points that you want. This is for sets. For graphs, you additionally to the node features, you predict edge weights or edge features. So first, I will talk about the update step because it's simple, and then we'll see the challenges of creation. For the updates, we have a set or a graph. We want to map it to another set or graph. So this is simple. This is the standard framework of equivalent networks. And depending on the order of the input, whether it's a vector, a set, or a graph, and the order of the output, all the functions exist and have a name. For example, if you have a graph, you want to predict a set, you use a graph network, you extract the node features. If you have a set, you want to predict a vector, just a deep set. One interesting one is if you have a set and you want to predict a graph, there is a paper that does it that is called set to graph. So it's something that we know how to do, which means that, okay, if we understand how to generate a set, then we can learn with it a set to graph function, and we will understand how to generate a graph. Okay, so that's why I will restrict the presentation to sets. Yes?
Yeah, but is that necessarily the best way to generate a graph, to first generate a set and then do set to graph? Maybe it's better to like create the edges and the nodes at the same time, because then they can, like the nodes also know about the edges that are going to be created, so to say, and not only the edges know about the nodes.
Yeah, you can. even if you have a set and you want to predict a graph, you will still update this set in the process. Okay,
Yeah,
so
yeah.
it's not that the set is fixed and you cannot change it anymore. So I'm not saying that it's necessarily the best strategy, but it's still flexible.
Yeah.
Okay. In general, if you want to go from order I to order J, we know how to do it. There is this great paper by Hagemer that I recommend if you've not read it. It's called Invariant and Equivariant Neural Networks. Okay, the only thing that we don't know how to do is how to go from a vector to a set, or how to go from a vector to a graph. And since we know how to go from a set to a graph, we'll focus on going from a vector to a set. And this is exactly what we want to do in the set creation step. Okay. So what are the requirements that we have for this function? First, we want a function that can output a varying number of points. And second, we want some notion of permutation equivariance, because we have this structure in sets, and we want to respect this structure, but it's not so clear what exactly we want. So for standard discriminative tasks, equivariance is well understood. You have this constraint that if you permute the input and apply your function, it should be the same as applying the permutation to the output. But if you want to apply this definition and your input is a vector, there is nothing to permute in terms of nodes in the vector. So the only equivariant function are the functions that predict all the points that are similar. Of course, it's not interesting at all. So it means that the standard definition of equivariance, it's too restrictive for generative models. We need to come up with something else. So what several people have proposed is the notion of exchangeability, which is that all the permutations of the output should be equally likely. It's a reasonable notion, but at the same time, it's not completely grounded. And especially if we generate a set, normally we should not care too much about the permutation of the sets that we generate. So we'll discuss later if this is really the right notion.
Yeah. Can we go over that again? Like, I think that's really one of the main parts of this paper, right? Like, why, if you now look at the permutation in your top row or your first bullet point here, the yeah, I can draw. Yeah, here, why are you saying that there it is interesting to just have equivariance? And yeah, why is it interesting here?
Okay. Imagine first that you don't have a latent vector, you have a latent set. Okay. How are you going to parameterize your decoder? You're just going to use a transformer, for example, which is permutation equivariant. So it's a permutation equivalent function, and it will map your input set to your new set in an equivalent way. But if you have a latent vector instead, the situation is different, because in a sense, the latent vector is invariant to permutations. Yes, Hannes?
Yeah, okay. Well, so can I just say, like, maybe I think if we just look at this example right here, if we just have a vector and we say that the inputs, like, no matter how, if we reorder the inputs, then the outputs of the functions have to be reordered in the same way. Why does that mean that the outputs are always equal?
Okay. So Z is a vector. For example, imagine that it's the solubility of the molecule.
Yeah.
Okay. The permutation doesn't act on this vector. So that's the first equality. And now if you try to impose equivariance, which is here 1 equal to 3, f of pi z equal to pi of fz. Yeah. Then you get that for any permutation, you are equal to f of z. Yeah. And so f of z, it's a matrix representing a set. So this means that all the rows are equal. Yeah.
Okay, good. I think we're all in the clear.
Okay. Okay, let's so we have seen that the challenging part is set creation, that okay, maybe we need exchangeability, but we'll discuss this. So let's see what people have done for creating a set or a graph. The easiest thing that you can do is just to learn a MLP. So you have your latent vector, you learn a huge MLP, and then this big vector, you reshape it in a matrix of size n max time another dimension, where n max is the maximal size in your data set. And if you want less points than this, you just mask this matrix to keep the first rows. Okay, so it's a very simple method, just learn a MLP and reshape. So it's quite fast to train when you try, but you're limited in the number of points that you can generate, because you cannot generate more points than the maximal number of points in the data set. You have this masking procedure. You mask the first rows, and why the first rows? It's something arbitrary that maybe you can improve. Performance is, I would say, surprisingly good for small sets, but you don't have the exchangeability properties that I talked about. Here, the permutations of the output are not equally likely. An alternative that is very popular is just to sample points i.i.d. I need n points. I'm going to sample them one by one. And this way I get a matrix. And then I will append the latent vector to the representation of each point. This is harder to train because you have a second source of stochasticity in the network, which is the sampling of the rows, in addition to sampling the latent vector. But the good thing is that theoretical properties are better because you can generate any number of points. You don't have this masking. You have exchangeability. But unfortunately, in terms of performance, it's not so good because it's very hard to train. You can say that it's because of the randomness, the extra randomness that you introduce in the network. You can also explain it if you write the math in the case of variational autoencoders. You can see that this method will only minimize a lower bound on the evidence lower bound, which is the standard thing that you optimize in VAEs. So you can also explain mathematically why it's harder to train.
Yeah. In the paper,
sorry?
In the paper, you also write a methods based on independent sampling use a Monte Carlo estimate for the gradient of the elbow that leverages the reparametrization trick. They therefore only optimize a lower bound of the elbow. And I like,
yes.
Why is this? Isn't this the case for all VAEs? That
okay, normally you optimize lower bound on the likelihood, which is called the elbow.
Yeah.
But here you minimize a lower bound on the elbow, so you have two inequalities.
Yeah, okay. I see there's the L dash is not the elbow. Yeah. Okay.
But okay, this is a previous paper by other people at EPFL. On the right, well, this random set is what I call independent sampling. So it's just difficult to train. No, there is a lot of stochasticity. So what they propose instead is the yellow one, and I call it first time creation. And the idea is super simple, is to have a reference set that is always the same. So you can train the entries of this reference set, but you will use it anytime you want to generate something. And then it's similar to the rest. If you want fewer points than the number of points in the reference set, you just mask it. And you append the latent vector to the representation of each of these points. You have the same issue that you cannot generate any number of points, but in terms of performance, it's much better. I would say that it was the best method that existed. Again, it didn't have the exchangeability property. And this is a bit surprising because you have the reference set you concatenate the latent vector to each point, and then you can do the update with an equivariant network. And it seems that nothing is wrong with this. It seems that you respect the structure of the set or of the graph if you want to generate a graph. So this method seems to be equivariant, but still it's not exchangeable. So what we've seen is that so far no method is very satisfying because the methods that work well, they don't have the right physiological properties and vice versa. That's the standard definition of equivariance that we use all the time. It's not suited to generative tasks. And in particular, this exchangeability notion, it doesn't seem to correlate with performance, which is not a good sign. So what I propose is to try to have another view of permutation equivariance and equivariance in general, and to propose a new definition that is more suited to generative tasks. So, okay, if we want a new notion of equivariance, what are we looking for? I would say that mostly we are looking for a way to make data augmentation unnecessary. That's what it is about, right? When you use a graph network, you don't need to use as input different permutations of your adjacency matrix because you know that if the network is equivariant, it's completely useless. And in let's take the example of graph networks. In graph networks, how do we get this unnecessary data augmentation? It's by using an equivariant network. This is the first step, but also by using an invariant loss function. For example, imagine that you have an n-body problem. So you have 3 particles, you want to predict their future state. Then your problem is rotation equivariant. And you want to use L2 loss in this case. You don't want to use L1 because if you permuted the input and the output, L1 loss would be different. So it's a bad choice for a rotation invariant problem.
Can you maybe elaborate on that a little bit? Why is it different if we use L1?
So if you use okay. Imagine that your prediction is wrong, okay? Mm-hmm. And it's wrong because you mispredicted the x-axis.
Yeah.
Now imagine that you rotate your inputs by 45 degrees because your network is equivariant. So the true target, of course, is rotated by 45 degrees because your network is equivariant. Your prediction is rotated by 45 degrees. Mm-hmm. But now, if you think of the location of the points, the L1 loss is not the same anymore.
Yeah. So
because it's the sum of the coordinates.
I don't know.
An absolute value.
We wanted to predict this location right here, but we predicted this location. And then if we rotate our all of our whole coordinate system, and then like let's say we rotated it around like this point maybe right here, and then our 2 points end up here and here, and the L2 distance would still be the same, but in our coordinate system our L1 distance is different than the L1 distance here. Okay, nice.
So nobody would think about using L1 loss in this case, okay? I'm not saying anything new. What I'm saying is that for equivalence, we need 2 components. We need to choose the model wisely, and we need to choose the loss wisely. Okay, what happens if you have an equivariant model, an invariant loss? Then if you write one gradient step, you can see that it will not depend on the group elements that is used to represent the data. For example, it will not depend on the rotation in the case of particles. So we propose to use this as a definition of equivariance. So we have an hypothesis class, a loss function, and of course a symmetric group. And we say that the pair FL, so hypothesis and loss, is equivalent to the action of the group if the training dynamics of the parameters do not depend on the group elements that represent the training data. And if you want to obtain this property in practice, you just need to write one SGD step and check that the parameters update. They don't change if you transform your input data. So for discriminative tasks, like the n-body problems that I talked about, we have that an equivalent model and an invariant loss, it gives equivariance. And for generative tasks, we can very easily derive sufficient conditions. It's just two-line proofs. In the case of GANs, you want an invariant discriminator. And then if you have the standard GAN loss, you have equivariance. And you have no constraint on the generator. If you have a variational autoencoder, you want an invariant encoder and you want a constraint on the loss, but you have no constraint on the probabilistic decoder. And if you look at the constraint on the loss that you have, it's something that is satisfied by what people commonly use for sets, okay? For set generation, the loss is usually either Schampfer or Wasserstein loss, and the two losses satisfy this property. So here again, I'm not saying anything new. All GANs based on all graph generation methods based on GANs satisfy these conditions. What I want to say is that we derived a notion of equivariance by looking at discriminative tasks. And this notion of equivariance is also relevant for generative tasks. This is first aspect. And second aspect, it doesn't require permutation equivariance in the strong sense that we use for generative tasks that I explained in the beginning. In particular, you see here that exchangeability does not seem to be needed. And to understand why, you just need to remember that if you want to generate a set, you don't really care about the permutation of the sets that you generate. All the permutations are equivalent. And if you think about the graphical model, there is this matrix to set function at the end that takes as input the matrix and returns the corresponding multiset. So that if you permute the matrix, the multiset is the same. So that's why exchangeability in the end, it's not needed. And it also explains why MLP is not so bad first. And also why first-hand generation is clearly better than independent sampling, which is an exchangeable method.
I need a second pass on that. Like, why do we, this matrix to set, you said remember what does, and yeah.
Okay.
You will go over there.
Okay. When you want to generate a set, what do you generate? You don't generate directly a multiset, you generate a matrix, n by d. And you say that each row, each of the n row is a point of my multiset. Similarly, when you want to generate a graph completely, you generate an adjacency matrix. But what you care about is the multiset or the graph, not the adjacency matrix. So if you generate a matrix that is always permuted in the same way, it's not an issue in the end because the corresponding set is the same. Is that more clear?
Yeah.
Okay.
Like it is. I think the first explanation was also good, but good to hear it. Good to hear it twice. Like it's a central point, I think. All right.
Okay. So what is the situation? So far, we've seen that we don't really care about exchangeability, at least for GANs and variational autoencoders. So it removes the main arguments in favor of independent sampling. But still, here, no method is super satisfying. In particular, in both MLP and first N, you generate a large set, and then you mask it in order to get a set of the right size. And masking the first rows, it's an arbitrary procedure. So if you could replace it by a differentiable mechanism, performance would probably be better. So that's what we propose to do, and we call it top-end creation.
So yeah, you're saying the issue is that if we just like in our MLP generation method, we just always generate 50 vectors with our MLP.
Yes.
From a random vector,
yes,
we create 50 vectors. And then we say we have our other categorical distribution because we know that at most we always want to create 50 vectors and at least we want to create 20. then in our categorical distribution, it now spits us out 30, and we just arbitrarily take the first 30 vectors that we generate. But
exactly, that's what is commonly done.
Yeah, but maybe in our molecule, we then don't even have the rights. Like one of the atoms corresponds to something else. Then, like maybe then we only end up with carbon atoms, right? So to say, and then
okay.
Yeah, but then afterwards we do the update steps anyways, right? So why is it important that we have a smart way of choosing the vectors if we do the updates anyway?
How to answer to this? Well, when you have a neural network, you don't want any of the components to be weak, right? Even if indeed you have extra layers afterwards, and you can learn to generate the right atom types and things like this.
Yeah, good.
But
so
yeah,
it is basically saying the if the set creation already is nice and chooses the right vectors, so to say, then the update part has to do less work.
Should be easier, at least. Yeah.
Good. And
but there is nothing stronger than this. I'm not saying that these other methods they have a very fundamental problem and that they can never work. But still, we can probably improve on them. Okay, so instead of picking the first points, let's try to have a mechanism to select the points that we want in the reference set. So we still have our trainable reference set, and instead of having one vector, which is its representation, we have a second vector as well, which we call the angle. And given the latent vector, we predict an angle as well. And then we will pick the points that align best with the latent vectors. So we just compute the cosines and we select the top n cosines. The issue with this is that selecting the top n cosines, it has a gradient of 0 almost everywhere. And well, it's not 0, it's not defined. So you cannot train this. You have problem of differentiability here. So you need to solve this issue, and the way we propose to do it, it's by using modulation. So this method, it was already proposed in the context of graph coarsening. So it was a slightly different context, but the mathematics is not exactly the same, but very similar. And the idea is that we are going to use the value of the cosines, and we are going to use these values to modulate the representation of the points. And now, because we use the value of the cosines, the gradients are not 0 anymore, and we can train the network. So if we look at the pseudocode, we have the latent vector, we predict an angle, then we compute all the cosines. We select the points that align best, that have the biggest cosine. And then we compute this modulation coefficient, C tilde, and we use it to update the representation. And in the end, we get x0, which is the initial set. So as I told you, modulation is sure to avoid having 0 gradients. And another advantage of top n creation is that now the number of points in the reference set is not fixed anymore. Before, it had to be limited to the number of points, maximal size in the data set. And now it's an hyperparameter that you can choose. Yes, Dominique?
Yeah, I have a few questions here about the method. Like, so the latent, basically you have a encoder and the decoder. The latent vector is the output of the encoder, and then in this decoder part, you decode a set, and you look at the cosine similarity between each of the nodes of the set and the latent and the global latent representation of the original graph, right?
Yes.
Yes. So in some sense, you're kind of forcing the nodes to be, each node contain all of the information of the graph in some sense, or most of the information of the graph.
Okay, that's how to say it. If you have a latent vector, your latent vector is going to contain only global information about the graph, right? Because you don't keep track of, if you had a latent set, it would be different. One point in your latent set could keep track of one atom in your initial molecule. But here, that's a general thing with having a latent vector, which is that you have to deal with global information. Then this latent vector, it's used at two different places. It's used to compute the angle and select the points, but also it's reinjected in the points. Okay. If you remember, sorry, I should maybe improve the figure. In both independent sampling and first and in the end, you concatenate the latent vector to each point. And here we do it as well. We just do it in a slightly more efficient way, and that's the last term, Z transpose W here.
But my point here is that, like, by you do the cosine similarity between this one and the latent vector, and this other vector and the latent vector again, and so on, right?
Yes.
Yeah. So
okay.
So basically, you only keep the nodes that, as an individual node, it has all of the latent vector, or almost all of the latent vector representation, because you're selecting high cosine similarity.
Okay, not exactly, because this is what you're saying is exactly what they did for graph coarsening. And the issue with this is that you will tend to select points that are all similar, because they should all be similar to the latent vector. But
exactly.
Here it's slightly different, because you, for each point in the reference set, you have two vectors. One is a representation and the other is the angle. So you can have 2 points that have a similar angle, which means that they are usually going to be picked together, but still they have completely distinct representations. So
yeah,
that's a way to avoid selecting only points that are similar to each other.
Yeah, but in practice, have you looked at what are the cosine angles of the vectors that you select here? Like, did you look? Did you see that the cosines are usually in a range between, let's say, 0.2 and 1, or they're all close to 1? Because it seems that with the back propagation here, the back propagation will push the values of the cosine similarity to go higher and closer to 1, and you can end up with all the node representation being the same.
Why would that push this? Because okay, this is all incorporated into VIE architecture, and what you optimize in the end is like a reconstruction loss plus a KL penalty, and it's not particularly good. You will not get a lower loss if the cosines are all 1. I didn't get this issue in practice. The cosines had a reasonable range, not really close to 1. But I don't see why they would converge to all the same representation.
Yeah, okay. Some sense, because by rejecting the low cosines, it's not forcing all of the cosines to become higher to not be rejected, or maybe I'm wrong. Like, maybe you have empirical evidence that it doesn't happen. So in that case, I guess it's fine.
Yeah, no, the cosines were tended to be small rather than big in practice. Yeah.
Okay. Okay, in that case, then it makes sense. Yeah.
Other questions at this stage?
Yeah, we have a question in the chat about the flexibility of the reference set. So how many reference vectors do we need to train if we
Okay.
want to generate graphs with up to 1,000 nodes, for example?
Okay. So as I wrote below, there is a trade-off there. You can choose the size of the reference set that you want. It's an hyperparameter. It has to be, of course, at least the maximal size in the dataset. But yeah, apart from this, you are free to choose it. What I observed is that if you have many points in the reference set, then each point is going to be selected less often. So training is slower in this case, which makes sense. But having more points in the reference set, it's also a way to avoid overfitting. So there is a kind of trade-off. The value that I would start with was twice the maximal size in the data set. But honestly, it's an hyperparameter and it's not super easy to choose.
Yeah, all right.
So if I want to generate a graph of size 1,000, I need at least 1,000 points in the reference set to answer the question. And Dominic is the number of points learned. So I told you that there are the two strategies. Either you sample n or you learn it from the latent vector. Empirically, I found performance to be similar. So in the end, I just sampled the size because it's just slightly simpler conceptually.
So that's,
so you can learn it, but I didn't really see an improvement.
Yeah, that's basically figure 1. Right?
Yes. Okay. 1 second. Let me up and paint again. Okay. We don't have the stochasticity issue of independent sampling with top n. Now, okay, we can choose arbitrarily the size of the reference set. We cannot generate more points than this. So we have some extrapolation power, but not infinite. We have replaced this masking by a learnable procedure that can adapt to the data. And so we'll check performance in a minute. One question that you can ask, which is valid for both first n and top n, is, okay, but if you start always from the same set, do you restrict expressivity? And the answer is no. If you have, because you have an update layer afterwards, if you use first n or top n, you can still approximate any set or graph. It's not a limitation. Okay, in terms of experiments, the idea is to say, let's look first at other methods and just try to change the set creation method. So we look at two methods, which are called TSPN and DSPN, deep set prediction networks. TSPN uses independent sampling, DSPN uses first n. First task is SetMNIST reconstruction. It's a set version of MNIST, like a point cloud with some noise inside. And it's just autoencoding. So what you measure is just reconstruction metric on the training set. It's quite basic. And so top n is better there. Then we have object detection on CLEVR. In this experiment, so we also use DSPN. We reuse their code. And there you measure performance on a test set. So it's still not generation performance, but it's not on the training set at least. Top n is better as well, especially in the full state prediction setting. I built a data set which I found slightly more interesting. The idea is to have a synthetic data set because, okay, evaluating a generative model, it's always hard in general. But if you have a synthetic data set and you know the generation process, then you can measure generation quality more easily because you know what you generated. So I built a data set points in 3D that look a bit like molecules. Like there is atoms are not too far apart, and the number of neighbors is constrained to look a bit like a molecule. And what you can see in general is that MLP and first N are slightly easier to train. They have better reconstruction metrics, but they tend to overfit. And the generation quality is not so good. Top N has better generation quality overall. And if you try to extrapolate and generate a larger set, then top N is clearly better. You can see here that independent sampling, it extrapolates quite well, but it's so hard to train that overall the metrics are not good. Finally, because all of these are set generation tasks, and I wanted to have a graph generation tasks by using the principles that I told you about. First, generate a set and then use a set to graph function. Of course, it's trained end to end. Okay, it's not a two-stage process. So I have a small experiment on QM9. In this case, you can see that this strategy is effective overall, using a set to graph function after set generation. But in this setting, I didn't really find a difference between the different generation methods. One reason could be that in QM9, almost all molecules have 9 heavy atoms, exactly 9. So it's not very important to handle properly the varying number of points, because all the molecules kind of have the same number of points.
Is that true? Like that all have exactly 9?
No, not all, but QM9 is basically almost an enumeration of all molecules up to 9 heavy atoms. And of course, the largest number is for 9 heavy atoms.
Yeah, okay.
So by far, it's dominated by molecules with 9 heavy atoms. So to conclude, the goal of this project was to try to set up the general framework for learning a set or a graph from a latent vector. FLU equivalence is a single notion that you can use both in discriminative and generative tasks. And for generative tasks, it captures interesting properties. In particular, if you use this definition, then it seems that exchangeability is not needed. I'm personally convinced that in these settings, it's not needed because you don't care about the permutations that you use to generate a graph or a set. Of course, it's hard to prove that something is useless, so it's just evidence, not a proof. And finally, top N creation is a simple tool to generate a set from a latent vector. And if you use it, then you can use what you want for the update step, like any graph network that you want or any equivalent network. Thank you for your attention. Do you have other questions?
Yeah, so why you say, like, am I missing something for the reason why you're saying that exchangeability seems like it's not necessary? Like, don't we?
Okay. It's a general problem. If you want to prove that something is not necessary, I have sufficient conditions for equivariance. For example, when you want to build a permutation equivalent network, you can use a graph network and you know it's going to be equivariant, but you can use a MLP that is not equivariant, and maybe by chance it will happen that because of the choice of the weights, your method is equivalent. So when you want to work on equivariance, you just have sufficient conditions. You cannot have necessary conditions. And here it's the same. So you can say that my sufficient conditions, they don't involve exchangeability, but it's not really a proof that exchangeability is never needed.
Yeah. Okay. And would you say that maybe there's a if we now want to make the perfect, like there's no reason why it would hurt, right? So if we want to make the perfect methods, there may be a way to have something like the or could the perfect method be, or could some improvement be to have something like the independent sampling, but we additionally have some yeah, or we get rid of the drawbacks of independent sampling, and we have the exchangeability of independent sampling.
Yeah, I agree that as you saw, top n does not tick all the boxes, so it's not the perfect method. It doesn't exist yet. Of course, it would be better to have even a better method. In my opinion, it's really a difficult problem. It's not really surprising that it's hard to beat good method for generating a set or a graph from a vector. For example, imagine the case where you want to generate molecules and you constrain the molecule on many different properties. Then it's not even clear that such a molecule exists. So it is a difficult problem for sure.
Yeah.
And for now, we don't have a perfect way to do it.
Yeah, I mean, it definitely is difficult and a tricky problem. And I really liked your paper laying out all of these, or laying out the space and explaining the problem and showing the different methods that people use there. And because I'm not in this graph generation topic that deeply, and yeah, it is a very very neat how people tried, or how you can follow what people first tried and what then worked a little better maybe. And now we have this first N generation where we have a learned way of choosing our, well, now no longer arbitrary vectors. Okay, but yeah, thank you for the nice paper in that sense, and also thank you for presenting it in such an awesome way and answering all of our questions. Any more questions or comments? If someone wants to say something.
Yeah. So thanks for the presentation of the great paper. One thing I want to ask, like, can you rapidly explain what is it that the set to graph does? Because I think that's something that that wasn't represented here.
Yeah, it's super simple, basically. Imagine that you have node features and you want to compute edge weights. Okay, that's the setting. There are basic operations that so the simplest thing to do is just to compute the vector product between your node features. Okay, so in the set to graph papers, they derive some operations that you're allowed to do. One of them is this. So in terms of matrices, it's an outer product of the node features. And the other operations that they have there is just broadcasting. So imagine that you have n by d matrix, it's your node features, and you want edge features. So it's n by d, okay? So you can just replicate your lines on both directions, or the other operations that you can do is take the outer product. They show that this is sufficient for universality, but it's super simple. It's what people have always done. They just it's a nice paper because they have this proof of universality, but in terms of method, it's what people typically do.
Is the broadcasting what people usually do? Because that seemed like I would just take the pairwise inner product.
Yes, the pairwise product is a more interesting operation in a sense, because broadcasting, it's not so interesting. It's saying that if I imagine that you're a node, it's saying that I'm a node and I'm going to have the same information for all of my edges. It's not very interesting in terms of at least in terms of application. But it's an equivariant operation at least.
But inner product also has problems that then it would mean edges only exist between nodes that are very similar. So
absolutely.
Well, that only happens if like we have a few update layers before it, right? And then yeah, why like we can't just learn whatever nodes we want. Like the nodes are only used for the edge creation in the end.
You don't need to learn one single edge weight. You can learn a bunch of edge features that each depend on part of the node features. And it gives you some flexibility. But if you're not careful, for sure, it's a problem that you're going to have. That you will have edges between nodes that are similar always.
Okay. I also have a question about this figure tree, like the figure about like the cosine similarities of the latent representation. Yeah, so
is it this one?
Yes, exactly.
Yes.
Did you check whether like these vectors here contain all of the information from the latent vector here? Like I don't know if there's the proper way, but like one thing I would imagine is that if the latent vector is obtained from a sum pooling, then doing the sum of these would and do a cosine similarity between these two should have something should yield something very, very similar, right? So here you would expect that if you did a sum pooling and then you're summing all of this, you should also expect a cosine similarity of 1. Did you do some kind of test for that or not really?
No, I didn't test it. They don't even need to have the same size. So it's not that easy to compare them.
Okay.
That's an interesting question because I have no idea how to solve it by hand. Like how to build an encoder-decoder architecture in which I have a sum pooling. So I have an invariant latent vector, and from which I will recover all my input nodes. It's not so clear how to do it. So it would be very interesting to investigate it further. So compare these vectors. It's not easy because they don't live in the same dimension, but it's definitely something interesting to investigate.
Yeah. Also, like these other vectors, like from the set that you generate, like because that's the thing, like you all have the cosine similarity with the original latent vector, and what you said is that if one vector is similar to one part, the other vector would be similar to another part, but that's not something that has been shown in the paper. So I guess like it would be very interesting to see if this is actually what happens. And I think like from this from doing this sum pooling and kind of inverse sum pooling to do the verification, it would be very interesting to know like if that's actually the case. And it could help also enforce the information to not get lost between the two, between the latent vector representation and the reference set that you generate. You also meant, go on, sorry.
No, I agree with you. So in general, top n manages better than first n, so it means that it's somehow able to select the points, otherwise performance will be similar. But how exactly, it's not so clear.
Yeah. So you said that you looked at the values of what the cosine similarities look like. Do you have them somewhere or not really? It's just like when they're developing, you looked at it to see what it gave you.
Yeah, no, it was more for debugging. The highest value was maybe somewhere around 0.5, 0.8. So here you have this angle vector. It's also the dimensionality of this space is also something that you can tune. Of course, the cosines depend on the dimension. The mean value of the cosines depends on the ambient dimension.
Yep.
So I checked them for debugging, checking that everything was right, but I didn't store them. Sorry.
Okay. Okay, perfect. I don't have other questions, but thanks again for the great presentation, and congrats on being at iCLEVR today.
Yeah.
Thank you for the invitation again.
I think then let's finish it, unless someone interrupts me. And let's finish it with Derek's statement. A very, very nice paper and careful reconsideration of the literature. I can say that's true.
Thank you, Derek.
All right.